Okay, thank you. Okay, thank you. So, as you all might know, in the oil and gas industry, flow assurance and production optimization are pivotal. So, software tools, including Pipesim by SLB, play a crucial role in modeling production system performance, supporting petroleum engineers in these endeavors. In this webinar, we are gonna delve into Pipesim's excellence as a top multi-phase flow simulator and its artificial lift modeling options. And also, we'll explore its fundamental features covering nodal analysis, artificial lift design, and optimizing surface pipeline networks for comprehensive production and injection system modeling. So now we're gonna present our host today. We have with us Mr. Ahmad Shammari, who is a senior petroleum engineer who boasts over 20 years of experience in production engineering, flow assurance, and digital oilfield solutions. As the product champion for Pipesim at SLB since 2017, he previously spent 15 years at Saudi Aramco, excelling in technical consulting and project management across diverse oil and gas optimization projects. With 4 patents in well modeling and reservoir performance monitoring, he earned his master's in petroleum engineering from KFUPM. Ahmed is an author of multiple SPE papers and actively conducts training for academia and the oil and gas industry. Thank you, sir, for being with us today.
It's a pleasure.
Thank you. And without further delay, let's start. I will leave a comment. If you have any questions, please leave them in the comment section, and we're gonna answer them later. Also, you can find the record of this session on our YouTube page. I will share the link in the end, and thank you.
Thank you, Yahya, and hello everyone. Good morning. I'm glad that I'm with you today for the second time. Basically, I need to start with the assumption that you have the basic knowledge of Pipesim well modeling, and if not, I really recommend that you go and review my previous presentation. Actually, I have several webinars on YouTube, and whatever I'm going to display right now again assumes that you already know how to build a well model. However, I'm going to quickly start by reviewing. So I have a well model right now. I'm gonna show you in a minute, but I'm going to quickly show you what are the data that are available in the well, and then I will build my tutorial or webinar today based on that, okay? So I'm going to share my screen now. And here we go. So I'm assuming that you can see my screen. So let's start then. Now, this is a well model, okay? And as you can see, the well is composed of one tubing. This tubing goes to this depth, which is 8,372 feet, with an inside diameter of 3.548. And there is also a casing. This casing extends up to 10,000 feet with an inside diameter of 5.791 inches. And this is the roughness, this is the wall thickness. Now, as you can see here, we have a packer. So this packer is to direct the flow inside the tubing. If I deactivate this packer, then the flow becomes tubing and annulus. If I also delete the packer, it will be the same. If I add a tubing plug, for example, then the flow will only be directed inside the annulus, okay? But let's go to our normal situation, which is there is a packer, and now at this depth, which is 9,817 feet, I have placed a single point completion. The main difference between single point completion and distributed completion is basically the assumption and how the IPR methods are used. Like, for example, if I say now the geometry profile is horizontal, then I can have different IPR methods. Babwa Nodi, Joshi, entry index as my IPR method. This is the reservoir pressure, and this is the starting point of my. This is the starting point of my inflow performance.
Sir, are you here?
Any
Sir, we have issues hearing you.
you know,
Sir, I think there is a problem. Oh, he got out. We will try to fix this issue as soon as possible.
what happened? Are we back? Yeah. Do you hear me? Because I see that, yeah, I do have a problem. It says no internet access. Do you hear me?
We can hear you now, yes, sir.
Okay. Yeah, sorry for that.
No, it's no problem.
Okay. So I'll probably just go and repeat the last few minutes. So as I said, this is the reservoir pressure. This is the productivity index. So this is my IPR curve. And for that, we have a fluid that is named as heavy oil. It has a very, I would say, low API, meaning very high density. It's a heavy oil and low gas oil ratio.
Sir, please. I'm sorry.
Oh, no, well, I'm not sharing, right?
Yeah,
Okay,
you're not
sorry.
hearing.
Okay.
Thank you.
Oh, sorry for that. Yes, so this is the fluid. So we have, as I said, low API. As you know, the API stands for the American Petroleum Institute, which is a unit that's used to measure the density. And I can, of course, use the dead oil density if I want, different units. The API, if it's low, that means it's heavy oil. If it's high, that means light oil, okay? And we have GOR, gas oil ratio of 202 stock tank, or standard cubic feet per stock tank barrel. And I don't have any surface equipment, meaning I am stopping at the wellhead. Very simple well model, not much details, no accessories or anything. It's just a tubing. This is my casing, this is my completion, and that's it. And we describe the fluid. Okay. Now, based on the fluid description and based on the reservoir pressure, based on the well depth, I'm going to construct my nodal analysis, okay, and see if the well can flow or not, okay? So, can you please unmute everyone, because I'd like to ask questions and probably people can answer me that directly, please. So now I'm going to run, okay? And then when this well runs, it says unconverged. Unconverged means it could not find a solution. And this is what we see. This is the inflow and this is the outflow. And the well, based on these conditions, based on the inflow and the outflow conditions, is dead, cannot flow. So my question to you is, I want somebody to describe to me by talking on the nodal analysis itself, why the well is dead. You can raise your hand or you can just unmute yourself and speak up.
Come on, guys, you can mute yourself.
You can unmute yourself. So my question is, based on these two plots, why do you think the well cannot flow? Pressure not available.
We can change size pipe, and we have a good velocity string to
No, but this is not my question. My question is why the well cannot flow now. What is happening here? Low API. Fine, but why, based on the inflow and the outflow, the well cannot flow? Based on just look into these two curves and describe to me, why do you think the well cannot flow? I need somebody who understands nodal analysis and describe, based on the nodal analysis concept, why the well cannot flow now.
We didn't have high pressure reservoir.
Okay, we don't have high pressure reservoir. Fine. But actually the pressure is good. 3,200 is high.
But yes, we have 320 pressure over our.
Yahya is saying there is no convergence between the IPR and the vertical flow, but okay. No convergence, not no convergence. Input not equal to output. Not clear. BHP too low. Actually, BHP is not too low. BHP is very high based on the outflow. Not aligned to our operating conditions. Still not the answer I want.
Sir,
So let me answer. Yes, go ahead.
If I may suggest, maybe it is because the inflow curve is way, or maybe the outflow curve is way above the inflow curve, and they should at least meet once.
Okay. That's obvious. I mean, even somebody, if he just knows inflow and outflow, can say that. But this is not so not sufficient formation pressure from the well. That's better answer. So let me just quickly describe this in 2 minutes. What does the outflow curve represent? The red curve, the red curve or the outflow curve represents the bottom hole pressure available or needed to push the fluid on these rates. Again, the red curve or the outflow curve represent the pressure needed to push the fluid in the tubing on these flow rates. Meaning, if I need to produce 1,000 barrels, then I need minimum of 3,550. If I need to produce 2,000, I need minimum 3,500. If I need to produce 3,000, I need minimum of maybe 3,490 and so on. So these points here represent the flow, the minimum flowing bottom hole pressure required to produce this flow rate on the x-axis. Whereas this IPR curve represents what? Represents the energy, the bottom hole pressure that the reservoir can feed if you produce these rates. Meaning, if you want to produce this 1,000 barrels, then looking into the reservoir energy, the pressure from the reservoir will give you less than 3,100. 2,000 will give you this pressure. 3,000 will give you this pressure. Okay? This means that the energy coming from the reservoir to produce these rates are lower than the minimum pressure required to push these flow rates inside the well. Is that clear? So now, in order for us to make the well flow, what we need to do? We need to bring this VLP curve down so that there is a point where the minimum pressure needed by the outflow meets the energy coming from the reservoir. So either we bring the VLP down or we push the IPR curve up. In either way, there is a different intervention scenario. So if I want to make the well flow naturally, the reservoir pressure must be increased. And to do that, I can simply do a sensitivity and I say, okay, currently the reservoir pressure is 3,200. What if I increase the reservoir pressure from 3,200 to 5,000? Then this will make the flow, this will make the well should not. So now if I make 5,000, it's not in here. Oh, sorry. I need to specify the reservoir pressure. So if I make these 2 points, 3,200 and 5,000, so I needed to define what's the parameter. And then I run. Then what do we have here? This line represents the IPR when the reservoir pressure was 3,200. Whereas this curve represents the IPR when the reservoir pressure is 5,000. So this is one method, which is to push the IPR curve up, right? Another method is to bring the VLP down. I can bring the VLP down by reducing the outlet pressure. But let me see if I can do that, because right now the outlet pressure is 300. So if I make it, let's say 20 psia, or just open it to the absolute, just 0 psig, for example. Okay? Now I'm just opening it to the atmosphere. Again, it's 300. Now what's going to happen? Let us see if we can make the well flow with this. So as you can see here, this is the VLP where the outflow is 300. And this is the outflow when I make the outlet pressure is only 0 psig. Okay. Now, of course, we need pressure. We cannot make the wellhead pressure 0 psig or open it to the atmosphere. That's why we use artificial lift. Okay. Now, let us start with the different artificial lift methods that we have in Pipesim. Okay. I'm going to start with the pumping. The pumping is a mechanical equipment that uses electricity in order to push the fluid inside the wellbore and play with the VLP curve. Okay. So the most common ESP design, and the reason it is common because it can cover very wide range of operating conditions and flow rate, is the electric submersible pump. Okay. Now going back to our IPR and VLP, what is the ESP going to do? So the ESP, the electric submersible pump, when I install it, I need somebody to tell me how it's going to solve this problem. If I install an ESP, what will happen? What will happen to the VLP, of course, because I'm going to add an ESP to the outflow, which means that it's going to change the VLP curve. So please, somebody answer me. What do you think the ESP will do to the VLP curve and how? Bring it down. How? How ya Saifuddin? Why it's going to bring it bring the VLP down? So let me just quickly I'm gonna type for you here. Edit. Edit. Oh, okay. So bottom hole pressure using the VLP, huh? Let's see if I can change the font. Yes, so I'll make this one, let's say 36. Okay, yeah. So bottom hole pressure equals what? Using the VLP, this curve here, the outflow curve, the red one. Bottom hole pressure at each flow rate equals wellhead pressure plus delta P friction plus delta P hydrostatic. This equation here is used to generate this VLP curve. Okay, so the bottom hole pressure. Now what do? For each of these flow rates, I'm going to calculate the bottom hole pressure to generate this red curve. Okay, now bottom hole pressure equals wellhead pressure plus dP friction plus dP hydrostatic. So what is the hydrostatic, dP hydrostatic? It's the pressure drop due to the density of the fluid. In other words, this one here equals so the hydrostatic pressure equals what? Equals density of the fluid. It's rho GH times depth times G, which is the acceleration term. Okay. Now, density. So by looking into this equation here, okay, and now I'm going now to install an ESP. So the ESP now is going to do what? The ESP is going to take, it's going to reduce the pressure inside the column by adding a pressure, meaning, in other words, the ESP is going to act on behalf of the bottom hole pressure. Okay, so this equation, when I have an ESP, will become BHP plus dP due to the ESP equals the rest. Is that clear what's happening? So when I add the ESP, okay, it's going to act on behalf of the bottom hole pressure, because the bottom hole pressure is going to push the fluid in the wellbore. All of these pressures are against this bottom hole pressure. The ESP is going to act on behalf the bottom hole pressure. If I rearrange, then this equation will become like this. Minus, and this is now what's going to happen when I add the ESP. So why the VLP curve is brought down? Because dP is negative due to the ESP. So for each of the flow rates on the x-axis, the wellhead pressure is going to be against, friction is going to be against, density is going to be against, but the ESP is actually going to act on behalf of the BHP, and that's why it's going to bring the VLP down. Clear يا شباب ويا صبايا? Everyone clear? So this is what will happen when I add the ESP. Now, how do I install an ESP in Pipesim? If you know your pump, you can simply go to the artificial lift and then simply artificial lift tab and simply click the plus sign, and then the equipment type is going to be ESP. Now you can simply, here's the ESP, you can put it at the end of your tubing, which is 8372, and then you select the pump type. For example, you're assuming that, okay, this is your pump. You click OK. And now the calculation option, I don't want to calculate the surface power correction. Now I need to define the number of stages because each stage is going to add a certain head. Okay. Usually each pump comes with a set of stages. For example, let me try that I'm installing 40 stages, meaning a pump after a pump after a pump. It's going to be very long ESP string. So by using ESP stages, I'm going now to run my nodal analysis again while this pump is installed, and I'll see what happens. So it brought the VLP down, but not enough. Okay. So now what I'm going to do, I'm going to increase the stages. Like, for example, let's go to 68, for example, and see what happens. Of course, this method here is just, without actual design. So right now, after installing this ESP, okay, I'm now able to produce 2,600. And then if I want to just to see the impact between the pump running and the pump is not running, I just go to the outflow sensitivity, go to the ESP, and then put the operating frequency, and then put 0 and 60 hertz. So 0 represents the ESP is not flowing or not running. 60 is operating. And now I will assume that I'm going to have two curves. One curve for the ESP not running, and another curve ESP is running. Okay. So this is how I install an ESP right away. However, there is also a way to design an ESP and select the best based on the catalog. So let's do that. So I'm going now to go to the ESP and delete it. And let's go to the ESP design. Here, there is a task here called ESP design. When I click on that, now it will first bring the current inflow and outflow. And this helps you to identify where do you want the production to happen. Usually, we need to focus on the intersection where the the inflow and the outflow is happening on the right-hand side of the VLP curve. Like, for example, for this condition, for this well, it will be nice that I can produce at 4,000. Because now this is on while the VLP curve is going up. So now I'm going to tell him, I want to produce 4,000 barrels. Now it created this line. And now when I click on this button, it will automatically list for me all the ESPs that can do the same. Like, for example, this is a pump Reda. It has the highest efficiency. And now when I say, okay, I will use this pump. Then I need now to calculate how many stages the pump needs to have in order to bring this VLP curve down to intersect with this point here. And this is a massive, actually, pressure, right? That's why I will assume that it's going to be a lot of stages. But let's run now. So when I click on run, you see it it found it, and then it says, okay, you will need 71 stages. And now it will show you all the results. Like, for example, it will show you the speed, which is the based on the rotation. You have the efficiency. You have the head added by the pump, the differential pressure. So this is how much. So it's going to add 800 psi across the pump, which means that it's going to bring the VLP down, and the difference will be 800 psi. This is the discharge pressure, okay? And I have different curves here. This curve here, this is the original IPR curve. This red one is the original VLP curve, okay? Now, the nodal analysis, the IPR and the VLP, I can place my nodal analysis point at any location in the production stream. So in this case, this represents as if the ESP or the nodal point is installed after the ESP, which means that in this case, it's going to affect the inflow curve and not the outflow. You see my point? So depending on the nodal point, the IPR and the VLP curve will be different. In this case here, this is the IPR at the location after the pump, okay, without an ESP, or with the ESP of you know, here this is the suction pump suction pressure, which means that this is as if there is no pump. This curve here is with 40 hertz. This curve here is with 50 hertz. This is the one which is I decided to install the pump for, which is 60 hertz, and this is for 70 hertz. Okay. Now, if I go to the actual pump performance curve, this is the blue line is the pump curve, the head added. So this is the manufacturer curve. This is the efficiency of the pump. And this is the power needed to, electricity needed to, you know, feed the pump at different rates, okay? This is the nodal analysis. So as you can see here, this is our IPR, and this is the VLP after bringing the VLP down. Now, if I'm happy with my pump, I just simply click on install ESP, and now the pump has been installed. Okay. Now, let us try to analyze some of the data here. So you will see that for each pump, there is a yellow box here. This yellow box represents what? Represents the minimum flow rate at base frequency, 3,500. The maximum flow rate at the base frequency. So you need your operating conditions to be around these flow rates, okay? And as the ESP frequency, the operating frequency changes, this whole curve will change, okay? When I go to the, there is also an option here called permanent magnet motor. This is a some special kind of motors, but I don't think it's relevant right now. If I go to the calculation options, I have different options. So number one, viscosity correction. This is to make the calculation more accurate. And as the pressure and the temperature changes across the pump, the viscosity will change. So by default, this viscosity correction across the pump is not taken into consideration, but I can activate the calculation so that it becomes more accurate. I can activate the surface power correction, or the calculation of the power at the surface. Gas separator present. So if I want to you know, remove all the gas from entering the pump, I can do that. And then there is also a more accurate calculation, which is stage by stage calculation. Now, I'm happy, so I'll go to my nodal analysis. The pump is installed. And now I'm going to run without any sensitivities. And let's analyze the data. So now, as you can see here, this is my inflow, this is my outflow. Now, I can go now to something called the profile results. In the profile results, I can see now the pressure profile with the elevation. And as clearly here, there is a jump in the pressure because on the x-axis it's pressure, right? So there is a jump on the pressure, okay, due to the pump, of course. And this is the wellhead pressure, okay? Now we can also go under profile results. I can go to show grid to show more results. Now we are starting here from elevation 9,000, which is at the depth and at the maximum depth. But let's also, just to be consistent with these numbers, I can go to select columns and add the measured depth. So click on select columns and I go to measured depth. And now you'll see this is the measured depth. As you can see here, this depth here represents the completion. So now this is the inlet. Okay. Now if I expand this plus sign, I will see all the results coming from the completion. So I can see the static pressure, the flowing bottom wall pressure, the drawdown across the completion, and so on. This is the liquid rate in stock tank barrel conditions. Now we scroll down. So this is the elevation. We're going up now, as you can see here, because this is minus 9,000. I'm going up until I reach to my pump. So this is my pump. Okay. The depth is 8372, as you can see here, 8372. And now I can expand my pump to see the different results all across the pump. So this is the pump, the power, surface power. So as you can see, since I did not add the surface power correction, so it's the same. This is dP, or the delta P across the pump. This is the temperature. This is the efficiency, and Q in, Q out. Okay. Now I want somebody to tell me why Qn, Q is the flow rate, right? Why Qn does not equal Q out? What happened? Where did the flow rate go? Did we lose almost 90 barrels evaporation? So why do you think Qn does not equal Q out? Speak up. Again, Q is the flow rate. We have Qn, and then we have Q out. But Qn does not equal Q out. Why? Any answer? Are you with me?
Yes, sir, we are hearing you.
Okay, go ahead. Inlet flow rate is not equal to the outlet flow rate. Why? Remains in the well. Interesting. Remains in the well. Okay. We have a pump. Flow rate going inside the ESP and then going out of the ESP or go inside the tubing. So it is IPR and VLP. No, it's not. This is only across the ESP, guys. So this is Qn, this is Q out. Efficiency of the pump. No. And by the way, to help you understand the question, It's Q pump. What do you mean Q pump? No. Look into this flow rate here. So this flow rate is represented everywhere, even at the surface. 4019. And this is also a third flow rate, different from Q in and Q out. Any question? Any answer? Guys, this is flowing flow rate, and this is the standard flow rate, S. Why the flowing flow rate is different? Because of the formation volume factor. Or in other words, due to compressibility. When I have more pressure, what will happen to the oil? It will be compressed, right? So its volume will decrease a little bit. Because now there is 800 psi added to the oil. So the flowing conditions of the oil make the well compressed. But at the standard conditions, it's all the same. So there is no oil that evaporated or no oil that remained on the well, or it's basically the same oil. It's just the conditions are different. So this flow rate is at pressure at the pressure inlet, which is in this case 2223. So flowing flow rate at 2223 is what? Is 84832. Now, when I added pressure at the flowing pressure became 3022, and that's why the flowing oil flow rate is less. Okay, I hope this is clear. Great. So now we have installed the pump. We are happy. So any questions on ESP? Otherwise, we need to go to another pumping method. Okay, if no more questions, I'm going now to delete my ESP. And now, let us try another pumping method. So, as you can see here, the default is PCP. Who knows what PCP stands for? ESP stands for electric submersible pump. PCP stands for what? Any questions? Any answers, sorry? PCP stands for progressive cavity pump. Let me show you what's the PCP. So if you go to the help, just type PCP, and then you read that it's a progressive cavity pump. When you click on it, this is a schematic diagram of the PCP. So the PCP is a big, helical rod, right? It's like a spring, but very extended, and it's a rod actually. And it's connected to an electric motor at the surface. So now, when this rotates, as you can see here, this rod is going to rotate. And as it rotates, okay, it's going to take the oil and the fluid as it moves up. Okay. So this is the progressive cavity pump. And there are some descriptions about how it works and so on and so forth. So now, if I'm going to install a PC, in Pipesim, we cannot design an ESP, a PCB, but we can actually, in a similar fashion, we can select a manufacturer. So like, for example, I can select a pump from the catalog, and you will see that the PCP has, as you can see here, the flow rate range is not really as high as the ESP. okay? And that indicates why the ESP, as I said before, is more common, okay? But let us select one of the highest flow rates. So what I can do is that I can double click here, and then this is probably the highest. So I'm gonna install this. Once I install it, okay, you will see now that we have different you know, operating conditions. Like for example, here, this is the diameter, this is the nominal rate, and this is the base speed, okay? So now I can I can go to the operating speed, and this is RPM, or rotation per minute, okay? If I say now 200, as you can see here, this is the curve, and now you'll see that there is a torque and the power, and there is also slip factor. So and now I need to also define the depth. So right now, let me put the depth at the end. So let's say this is going up to 8372. That means it is extended. So this is just a symbol. However, in the middle, there is the shaft, okay? So now let us see, by using this PCP, is it enough to lift the oil, right? So now I'm going to run. And here we go. So the well now, this is the, we just zoom in, okay? This is the inflow and this is the outflow. So in a similar fashion, the PCP brought the VLP down, okay? And also I can do a sensitivity, like I can go to the PCP, and then I can go to the operating speed, and I say, okay, what if the operating speed is 0? This represents that the PCP is not working. And I put 200, which is my, you know, current operating speed. And now I click on run. See here. Okay. So yeah, I mean, it has to be. If we just the PCP needs to be. We just put probably 100. So as you can see here, this is at 100. It's barely making, you know, the production, and this is at 200. Okay. So this is the PCP, the progressive cavity. It's one of the common, you know, pumping methods, but of course not as the ESP. The third one, which is very common, especially in low flow rate or low pressure reservoirs or shallow reservoirs, is the rod pump. So what's the rod pump? The rod pump is, of course, you can also go to the help, and then you can type rod pump to understand more about the rod pump. So this is the double click here, and then let me see if we have a good representation. Oh, no. So anyways, the rod pump, unlike the PCP and the ESP, is not rotating. So it's basically based on what's called volume displacement. Okay, it's rotary, it goes up and down, right? And you know, it has a you know, it isolates up and down, and then it has a valve, two valves actually. The one opens at the bottom, one opens at the top. When it goes down, the bottom valve will open, so that it goes and holds on certain volume, then the bottom valve will close, the upper valve will open, and then it will, while it moves up, it will push basically the fluid. And it's as I said, it's classified as positive displacement method, and you will see it everywhere. These are the ones that have small rotary or small speed movement. You see it a lot in the US, you see it in China. Sometimes you see it in the Middle East, but not very common, because these pumps actually operate on much lower reservoir pressure conditions and much lower flow rates. Now, there is let me just for the sake of I need to use better data. I can go to the help case studies, and then you see that there is under well models folder, there are some examples. One of them is for the PCP. So you go here. So this is for the rod pump simulation. So click on open, and now, so this is a well with the rod pump. So right now, you can define the rod pump either by the nominal rate or the stroke length frequency. Like, for example, here we have 12 strokes per minute, which means that we're talking about roughly every 4 seconds there is a stroke, right? So this is kind of one of the on the high side of ESP or rod pump pumping. This is the stroke length. So when it rotates or when it moves up and down, it oscillates, it goes down by 108 inches. Or in other words, if I convert this into meters, you can say that this is only 2 meters. Okay, so this represents the length of the stroke, right? There is a plunger diameter, and when I run this now, I go to the nodal, and then there's also slip coefficient, the one that can be used to adjust the flow rate, because as you know, the since it's a rod pump, as it moves out, right, there is always some kind of liquid that is not completely shifted up, and that's why we call it the slip coefficient. This is the inflow and this is the outflow at different slip coefficients. Okay, as you can see here, the flow rate here, we're talking about in the range of 100, 200, 300 barrels per day. Okay, so even if I go to the completion, you will see that the pressure is low, and we're using here Vogel correction. The absolute open flow is 520. So this is as you can see on x-axis, it's on the range of hundreds, not thousands. Okay, so these are the different pumping methods: ESP, PCP, and rod pump. There is a fourth method which is available inside Pipesim as a plugin. What do we mean by a plugin? The plugin is not a core functionality in Pipesim. It's developed as an example if somebody wants to extend Pipesim capabilities. How do I add this plugin? You can basically go to Workspace and then Options. Under Options, you see something called Plugins. So now I can register a plugin. So the plugins there are some example plugins that are already coming with Pipesim. So when I click on Register, you can go to this folder here, and then if you go to the Developer Tools, and then is it User Equipment? No. I think Pipesim Labs, sorry. Then you see these are plugins. So one of them is called Jet Pumps. Okay. So what is a jet pump? See, now it's a DLL. This is now external, meaning outside of Pipesim. This shows you that Pipesim can be extended in the calculation. So, and there are, of course, documentation if you want to develop your own. So when I click on Open, now the jet pump has been added. And I click on OK. Now, I will simply delete the rod pump. How do I add this jet pump, which is a plugin? So there is under the insert button here, insert tab, sorry, there is something called user equipment. And since I have registered now the jet pump, I can simply click on it. And then I can bring it here. So what is the jet pump, guys? The jet pump is a pump that is working by injecting gas in a high speed. This gas is going to reduce the pressure. So it's not like gas lift, because gas lift is actually playing on reducing the density. This one here is also affecting the density, but the main mechanism is by reducing the pressure due to the very high velocity across this pump. Okay, so yeah, as you can see here, there is a nozzle. Okay, there is a nozzle. There is a nozzle that makes the fluid that passes through this pump very high velocity, and then due to that very high velocity, the pressure will be less. Then these are some other parameters. This is the power fluid pressure, and then now it's asking us about what fluid are we using. So we need to add gas. So I'm going to add simply dry gas and click on OK. And now click OK again. So now it has added the fluid. Now when I go to my basically nodal analysis, when I click on run, so this is the using the because I was using the original the one that was working for the rod pump. So let me just improve the completion a little bit. Let me see if I have a jet pump in the case studies. No, I don't think I have it. So anyways, we can, of course, if I want to make this well flow better, I can simply go to the completion and play a little bit. So I'll make the reservoir pressure, let's say 4,000, and then I'm gonna increase the absolute open flow. So now this is our IPR. Now when I go to nodal analysis and go to reset boundary conditions, click on run. Then we have this conditions. I can go, of course, to the profile results, okay, and then show grid. And now you can see here I have the jet pump here, and this is the no, it appears that we need to rebuild it. This is the newer version. It needs that the plugin was not updated, properly, so that's why you don't see the results here. But anyways, this is because it's a plugin. It's not a core calculation inside of Pipesim. But this is, as you can see here, we have now shown 4 pumping methods: ESP, PCP, rod pump, and the jet pump. Okay. Now the last artificial lift method is the gas lift. Okay. So now I'm going to go originally to my case, and then let's start with we're talking about gas lift and how gas lift works. Okay, so now in this case we have a well. Let me just delete this gas lift valve. I'll go to the completion. This is PI. Okay, PI is 8, and then this one is 3,200. Okay, so this was our original case, I believe, and then when I go and run, the well will not flow. Okay, so now in this scenario here, we need to bring the VLP down by another method. not by a mechanical pumping, but using the gas lift. So can somebody quickly just tell me, based on these equations here, okay, how the gas lift going to affect our VLP curve? Similar to what we talked about for when we explained the ASP. So based on this equation here for the outflow curve, how the gas lift is going to help us produce more. Reduce the density. Excellent. So now, Pipesim in the gas lift design is really powerful, and you can do a lot of gas lift modeling by either trying to see the impact of the gas lift rate right away, all the way up to designing a full gas lift system. So what I'm going to do right now is that I'm going to insert a gas lift valve. So this is gas lift. I'm not going to do design now. I'm just going to click here, and then I'm going to put a gas lift valve as deep as possible. Now, the injection quantity, I can say now, let's inject 1 million standard cubic feet per day. And this is a common value for injection. I'm not talking about how much pressure do I need in the surface to inject this, what kind of valve I'm using. I'm just using fixed injection ports, meaning I am telling the software that I am at this depth, inject this amount of gas, just as a preliminary design or preliminary calculation. So when I go to now to the nodal analysis, see if that will help, okay? It worked actually. So now the well, by simply injecting 1 million at this depth, it is going to flow. And the reason it's going to flow is because my main problem in this well is that the fluid is heavy. I have very high density due to the low API. Just to remind you, this is our fluid. So the fluid that we have in this well has a very low API, which means very high density and low GOR. By playing with the gas, this will, of course, going to bring the VLP down. To see the effect, let's go to the outflow sensitivity, go to the gas lift valve, and then I'm telling him, okay, the gas injection rate, 0 and 1. Is it 1 or 2? Did we say 1 or 2? 1, okay? So now, this two cases, as you can see here, this represents the 0 flow rate, the 0 gas injection. This represents the injection with 1 million, okay? Now, this is the minimum. This is, as I said, this is the one of the very quick tasks to examine gas lifting into your well, okay? The second method, or the second level, is that you can, by using this injection valve, you can determine the stability of your gas injection valve system. Now, you go to something called Al-Hanati stability check. Now, once you enable that, it's going to ask you about the surface injection pressure and temperature. So now you tell them, okay, I am the surface injection pressure and temperature. Now it is asking me about the port size. They didn't ask me about port size before. So let's assume that it is 0.125 inches. And then I'm now not going to run nodal, but I'm going to run PT profile right away. Okay, basic boundary conditions. PT profile is just pressure temperature, just one gradient. Okay, so click on run. Now I go to the show grid, and then if I expand this now, I can see now the flow rate. I can see the injection point temperature. This is DP. Okay, and now if I go to there is something called output details. If I scroll down, you can see this is the injection gas, okay? And then based on the casing, now you see the casing pressure required is 3,500. And sorry, the casing head pressure is 2,700, okay? And now the casing pressure that I have entered is 1,500. This indicates that you will have a problem, okay? So again, this is just another level. And of course, I can go more and more. Like for example, if I want to do a proper gas lift design, I can delete this fixed injection port, and then I can go to the gas lift design. For the gas lift design, this is the proper sophisticated gas lift installation. So now there are a lot of information I need to enter, okay? Like for example, I can go to the production outlet pressure. So in this case, it's 300, okay? Unloaded outlet pressure, not important. This is the reservoir pressure, temperature, GOR, water cut. And now it is asking you, okay, what is the operating injection pressure? So at 1500, now this is my available surface injection pressure. How much do you want to inject? I will tell them I want to inject 1 million, because I know that 1 million has worked before, right? So now many of the other options, like for example, include friction. There is the spacing control using IPO. So IPO, so the valves, because now it's going to find actual physical valves for me, okay, to be installed. There are different types, of course. Like for example, we have a type called IPO. IPO stands for injection pressure opening. It meaning that it will the valve will open based on the injection pressure in the casing. There's another type, which is PPO. PPO stands for production pressure opening, right? It's either based on nitrogen or a spring. This is a bit advanced on you, but just to describe the idea. So now if I go again to IPO, okay, there are a lot of advanced parameters here for the design bias, the test track temperature, and now this is a new feature that we added in the latest release 2024. You can generate even the report for your design. So once I do this, most importantly, I need to define these boundary conditions. How much is the operating pressure? How much you want to inject? And then you need to select what kind of valves you want. And then when I click on run, it immediately found the valve combinations, okay? And now as you can see here, this is what we call the gas lift design report, or the gas lift design plot, okay? This is just to learn a little bit about this curve. So number one, this line here represents the liquid level pressure. What is the liquid level pressure? So you remember the well did not flow, right? The well did not flow. Why did not flow? Because the fluid is heavy. So now without the injection, the fluid is stagnant in the well, and it is at this depth, which is 2000 plus. So this is just the fluid gradient inside the well, okay? This curve here represents the casing gas pressure. So if you remember, we said that, okay, the injection pressure is 1500, right? So now that's why you see that it starts from here. And this line here is the gradient of the gas, because we defined the gas specific gravity and we said include friction. And we said I need to inject one. So now it's going to calculate this line here, okay? Now, there is what we call the unloading valves, okay? So now the unloading valves, you need to draw parallel lines to the stagnant or the original you know, slope of the fluid inside the wellbore. So if I go now to this you know, line, and then I'm not sure if you have taken this in the university, but you need to use like a you know, a ruler or something to slide a line that is parallel to this, okay? And then you try to find the intersection. There is, of course, a differential pressure, and then this is your pressure. So this is operating pressure, okay? So you go to the operating pressure, and then you draw a line. This is the location of the first valve. Then you start going by drawing in a horizontal line, and then you take you know, a parallel line here. This will define your second valve. This is your third valve, and so on. And now this is we have now 3 unloading valves and 1 operating valve, okay? If I'm happy with this, I can go to the grid here just to see how the well will flow. So now, based on these conditions, the well is going to flow 2500. The deepest injection point is 5600, okay? And now we are going to inject 1 million against this casing head pressure. If I'm happy, I can generate a report. This report is going to be, you know, I can generate it, and then this can be given right away to the field. So if I now go to it will open now. So this is my report. So as you can see here, this is the input data, this is the design results, and this is the report, the graph. If I'm happy with everything, I can install the design and now close. As you can see here, it has now changed into injection valve system, and it has installed the different gas lift valves, okay? Now, if I want to run, I can run right away, but there is also another level of being more accurate, more advanced, is to enable multi-pointing calculation. So multi-pointing is a case where you'd like to avoid as much as you can, but it could happen. What do you mean by multi-pointing? You would like all the gas to be injected at the most bottom valve, because this is the best efficiency, right? So now I can, if I click on enable multi-pointing, and I tell them, okay, do the calculation using the fixed injection pressure. Now, when I go to PT profile, for example, and I run, now I can go to the diagnostic results. It will tell me now, if I go to show grid, it will tell me now if I have multi-pointing. So in this case, I have multi-pointing. I have 2 valves that are you know, open, and they are throttling. So now that means I need to you know, improve my design. I can go back and do another design, or I can say, okay, what will happen if I'm going to increase the surface injection pressure? Like, for example, what will happen if I say, okay, let's instead of 1500, let's increase this and make it 1600, and see if that will you know, improve the situation. So now I'm producing much more now. Go to show grid, or I can go again to the diagnostic results, show grid, and now I have 3 valves that are open, but they are not throttling, okay, which is better, but still it is it's multi-pointing. So I would like to also avoid that situation, so I can go back. So the gas lift design is a process that is iterative. You will need to play with a lot of parameters to get your optimum design, but once you're done, it's very effective, because gas lift, once you have the enough investment that you have, you put a capital cost, but then the operating cost is really much less. Okay, so now in this case I go to diagnostics, and let us see what do we have here. So now we're having, so it's not a good design, of course, because now only one of the gas lift unloading valves is running. So now I can probably, maybe IPO is not the best gas lift valve type for me, so I can go there and change it. So as I said, it requires some experience, it requires some knowledge about your available type of valves. But once installed, as I said, I mean, this is one of the strength point about Pipesim, because it will tell you after you install your gas lift valves what are the valve conditions. So I think this is it. One last point I'd like to mention is the optimization of your network. Okay, so let me just show you quickly. If I have a network of, let me see here, network models, ESP gas lift optimization, or ESP optimization. Okay, so after you have installed your artificial lift system, you'd like to know how much is the optimum frequency. Okay, in this case here I have a system where let me just go and make all of the pumps are having a frequency of 60. So now let me just go here, and then so this is 60. This is 60. So I have a system that's composed of 7 wells, with each with an ESP. And now if I run this network, finally this one. So now these pumps now are operating at its base frequency. Meaning, if I go now to my network, and then I run my system, you will see that these are the, if I go to the manifold, which is this is how much the total production here. It's this oil to sale. So this is my sink. So I'm now producing oil 758. Okay, and out of that I have 3,000 barrels of water. So very high water cut. Okay, with lower oil flow rate. So now this is the reason, is because you will notice that the wells, each well, okay, have different water cut. So there are wells that have very high water cut, and the water cut is not the same. The pressure of each of the wells is not the same. So now I would like to see if I can increase the oil production by just playing with the ESP frequencies, okay? So how do I do that? I will probably just put this task aside here. I can do this by going to the network optimization. So the network optimization, in the beginning, this is the ESP, this is the reservoir pressure for all the wells, okay? And now, as you can see here, if I go to the initial conditions, all the ESPs now have ESP frequency of 60. I can put constraints. Like, for example, what do you mean by constraints? I can put limits. Like if I go to the sink, I can go to, specify certain maximum flow rate or whatever. And if I go to an optimization control, now I would like to maximize oil rates. So the objective for me right now is to maximize oil rate. However, I would like also, if I go to the, constraints, I need to, to go to, I need the sink to be limited on water production, right? So if you recall, I was producing 3,400, and this was our oil production. So my question is, can I limit this water production and increase the oil production? I don't know. So what I will do is that I'm going to tell them, okay, maximum water rate is probably 3,000. So what will happen right now is that the system is going to play with the ESPs, with the ESP frequency. This is the control variable. And this is the fixed power. So this is the power that I have right now. I need to distribute among the pumps. So when I click on run, now what will happen is that the system is going to generate what we call well curves. Well curves are to represent the well response at different ESP frequency, and then it's going to optimize. It's going to play with the ESP frequencies but of course I gave them a harsh condition, which is I don't want the water production to exceed 3,000. Although in reality, when all of the pumps are actually operating at 60 hertz, we're producing 3,400 barrels of water. And this was our initial oil production. Okay. So now it has created the curves. Let us see if it will be able to match. So as you can see here, it did not accept, it wasn't able to limit the water production because the water cut is very high. So now what I'm going to do, because I have a water cut of 81, so if I want to maximize oil production while maintaining this limit, it's impossible. So now what will happen is that I'm going to remove this limit, and then I'm going to click on run again. So this is after we installed the artificial lift system. I'd like to optimize my operating conditions across the full field. And this same method applies to gas lift rate, to PCP speed, to rod pump speed, and so on. So now it was able to increase the production by 1%. So 1% compared with the original one. So as you can see here, the original oil flow rate was 758. It increased, it wasn't very successful, and this is because of the high water cut. But now it now calculated the new ESPs for me. So the distribution of the ESP now has changed. And then you will notice that the wells that have, high water cut, it has reduced its frequency, okay, and it went to the wells with low water cut, and it it increased its frequency. And just to show the let's say the good impact, what if I go here and reduce the three, let's say these three wells, I'm gonna reduce the water cut, okay? So I go to the completion, and now fluid model, let's make this one 0, okay? I'll make this one, completion is 0, and this one also, I'll make the completion, sorry. So I'm gonna put 3 wells that have actually, I'm gonna reduce the water cut. So now, if I go to the optimization now it's the same objective. And let's say that if I go to my options, now for the optimization control, I tell them, okay, I have more power. So I'm gonna distribute 700, okay? And now I can now go and to my sink, and I tell them, okay, now can you meet this condition? If I have wells with lower water cut, see, now it managed to increase the oil unconverged, unfortunately. Seems that this condition here is very harsh for the just okay. The optimization is works much better when I have bigger network, because it has more degrees of freedom. This network here is just for demonstrating the purpose. But in reality, of course, we don't have a network like this in the field. So it is converge now, and let us see the ESP distribution. So let's see now, if I go to, so this is the frequency, okay? So these are the wells that have lower water cut. See here, it has lower water cut. Now it has increased those, and let me see here. Oh, this is fixed power, that's why. Okay. Anyways, I'll it's I can of course fix because I'm forcing it to use all this power, so they don't have freedom. So the best option is to tell them maximum power is this much. But anyways, this is just to describe the ability to automatically distribute the artificial lift quantities. If I don't have artificial lift, I can also play with the chokes automatically, so that I can maximize my production with my constraints. With that, I think we have already exceeded the time, so we can open up for questions if you have. Otherwise, I'd like to thank you very much for today's session. If you want to learn more about, artificial lift options, you can always go to case studies, well models, and then you will find different options here. Like, for example, I have ESP simulation, dual ESP system, composite lift, PCP, and then, this is the design. These are different gas lift examples, okay? And so on.
Thank you, sir, for your presentation. If you have any question, please leave them in the comment section.
Okay, I guess that's it.
Okay, so thank you, sir, for this delightful presentation. And as a production engineering student, it was very interesting to apply the theoretical informations I have and see them being used within the software, and also to explore the large panel of possibilities it offers. So yeah, thank you, sir, and thank you everyone for assisting this lecture, and I hope to see you with us in the future lectures and events.
Okay, thank you all.
Thank you, sir.
Bye.